Professor Summer Madanat. Let me introduce him. The Summer is the Zeno Distinguished Professor and Chair of the Department of Civil and Environmental Engineering, and also the Director of the Institute of Transportation Studies at the University of California at Berkeley. He received his bachelor degree in civil engineering from the University of Jordan in 1986, and a master and PhD in transportation systems from MIT in 1988 and 1991, respectively. His research and teaching interests are in the area of transportation and infrastructure management, with an emphasis on modeling facility performance, the development of optimal management policy under uncertainty, and the integration of sustainability considerations in the transportation management process. He has published extensively in regular journals and conference proceedings. In 2000, he received the Science and Technology grant from the University of California Office of the President, and award given annually to one faculty member in the UC system. From 2001 to 2010, he served as the editor-in-chief of the ASC Journal of Infrastructure Systems. He is a member of the editorial board of several technical journals. Many of his former students are faculty member at university in the U.S. and abroad. With that, please join me in welcoming the Professor Madanat to the talk.
Just as a point of clarification, I'm no longer director of the Institute of Transportation Studies. I stepped down this summer.
Okay.
Because I found that being both department chair and director of a large research institute led me to do both jobs poorly, as opposed to just one job. All right, so when James invited me, he thought it would be interesting maybe for me to describe some of the more recent research I've been involved with collaborators at UC Berkeley at the intersection of transportation systems and sustainability concerns. This is part of a major research effort in the UC system, not just at Berkeley, in response very much to state priorities as well as global concerns having to do with greenhouse gas emissions and energy consumption. There's been significant work done in the transportation sector on reducing greenhouse gas emissions through alternative fuels and different vehicles. There's been less work done in trying to reduce the impacts of civil infrastructure. And the type of infrastructure specifically I'm concerned with is that of transportation infrastructure, primarily vehicles. So the research that I will be describing looks at ways in which, through better management of existing highway pavements, it is possible to reduce greenhouse gas emissions and to find ways in which greenhouse gas emission reduction becomes part of a decision-making paradigm for the management of existing highway pavements in the state of California specifically, but applicable certainly more broadly. So this is what I'll try to describe. The abstract of my presentation had the second component where I was going to look at a similar approach in the design of urban public transportation, but James advised me that I had less time than I thought, so I'll leave that aside and I can refer you to additional papers. So I'll talk a little bit about pavement roughness, which is very much at the heart of that sustainability of that greenhouse gas emission question. Describe a little bit what pavement management is, starting at the facility level, and then bring in greenhouse gas emission as part of pavement management. First, again, facility level, then we move to the system level problem, which is the problem that state agencies face with hundreds of thousands of kilometers or lane miles, and some policy analyses that we can do with the framework that we developed. This is a list of references that describe our work in this, and the first group of papers describe mostly are relevant because these are the kind of optimization approaches that we have used in this work. Much of them were developed many years ago as part of our emphasis at that time on life cycle cost minimization. And the last two are more focused with them bringing in life cycle impacts as well as life cycle costs into the decision-making paradigm. So the motivation I described briefly, I mentioned the priorities in the state of California. These are law in the state of California. Assembly Bill 32, has mandated that the state of California should reduce its greenhouse gas emissions by 2020, so only in 5 years, back to 1990 levels. And this is law that all the state and in general, all public agencies, cities, municipalities, and the private sector are supposed to do their part into that. There's an executive order from the governor that took this and provided additional details and additional mechanisms for making that law applicable, having to do with things like cap and trade, for example. Now, why is that relevant to Caltrans and to the transportation? Caltrans is the California Department of Transportation, and the transportation sector in general is in California. It is the second largest source of greenhouse gas emissions. In the US, it is the third as a whole at the national level, but in California, with its very extensive system of highways, it is and very high volumes of vehicle miles traveled, VMT. In California, it is actually the second largest. So, as I said, at the heart of all of this is something we call pavement cost. Now, highway pavements have a number of distresses and failure mechanisms. There are things like cracking, raveling, rotting, potholes, which are really an extension of cracking and raveling. All of these matter to state agencies when they're making decisions about maintenance, rehabilitation, and reconstruction. But the most important measure of performance is really roughness. Roughness is a collection, is an aggregation of all of these things. And it matters because this is what affects user costs the most. In particular, and of great interest to us, roughness matters very much to fuel consumption. It of course matters to things like comfort, vehicle wear and tear. In the case of agricultural products, it leads to potentially loss and damage and significant economic losses as well for very high levels of roughness. But most importantly, in our context, is fuel consumption. Now, roughness is affected by a number of things. The structural characteristics of highway pavements, environmental effects will play a role, like precipitation, freeze-thaw cycles, etc. Now, roughness is typically measured in most countries, including in the US and most states, in IRI, that is the International Roughness Index, either in meter per kilometer or inches per mile. And it's described essentially as the vertical displacement per travel distance relative to a perfectly planar surface. Another measure of roughness, which is less used nowadays, is the quarter tower index, and they're somewhat related. There's this approximate relationship of 1 QI is 17 IRI, or rather, no, it's 17 times IRI. So 1 unit of IRI is 17 units of QI. So what do highway pavements, what can they do to combat roughness, to eliminate it? Well, the two basic alternatives is to do nothing. Do nothing leads to an increase in rolling resistance, which leads to an increase in fuel consumption, that is a decrease in fuel economy, an increase in vehicle wear and tear, and an increase in the subsequent rate of deterioration. Resurfacing, which essentially most of the time consists of milling the top surface of the asphalt pavement and then filling, or mill and fill overlay, or mill and fill resurfacing, and adding a layer of asphalt concrete, typically of equal thickness to the one you've removed, but possibly larger or smaller. That reduces roughness and of course increases material and construction costs. So essentially what you have is a trade-off, right, in making the decision on when or how frequently to overlay or to resurface is a trade-off between the agency cost and the user cost, right? And so most highway agencies have policies on to make decisions when to resurface a highway pavement. In many states, including in California, this decision was made essentially on the basis of something called the trigger roughness, or the threshold roughness. And this mandates a certain level of roughness at the point at which an overlay is necessary. Caltrans uses currently a 2.7 meter per kilometer IRI as a trigger roughness. In the past, they used a higher roughness, 3.5. It's used uniformly for all highway pavements owned and operated by Caltrans, right? So it doesn't matter whether this is an interstate or a small rural road. These are the trigger, or the higher is the trigger roughness they currently use. Washington State DOT, for example, uses a higher level, 3.5 meters per kilometer. Two questions, of course, is that are these based on any kind of economic analysis? Is that optimal in some sense, that trigger roughness? And the answer is, at least in those states, it is not. It's based on subjective criteria of what is the maximum tolerable discomfort. And so there's no real optimality embedded in that number. And the other question, and also an important one, is should all roads be treated the same? That is, should we use a universal trigger roughness? That's a question that we also thought should be answered. So our objectives, we develop a framework that we can use to do some policy analysis, that we can, through which we can identify various means of combating greenhouse gas reduction from the transportation infrastructure. The scope, to be precise, we're only looking at asphalt pavements, not concrete pavements, the black top, not the white top. We're not considering minor pavement maintenance or reconstruction. Reconstruction is a big deal, but it's done very, very infrequently. And so, though we're actually currently, in our current research, looking at reconstruction, we're focusing exclusively at overlay, not the reconstruction of the entire structure, right? And when we look at the roughness effect, we're looking on the vehicles, we're looking at fuel consumption and vehicle wear and tear. Other things like comfort are not really quantified. So, where do greenhouse gases emanate from? So, typically, in civil engineering, certainly, our focus has been on tailpipe emissions. Now, while tailpipe emissions are an important part of the total production of pollutants, one needs, when one looks at greenhouse gas emissions and criteria of pollutants, one needs to look at the entire supply chain of various phases of the life of a pavement and a vehicle. So these are various sources of greenhouse gas emissions, many from the use phase, but many earlier, before even the use. That is, it's not sufficient to look at a pavement as it exists now, but to look at the entire process of materials extraction and production, all the way until the use phase, and in cases for the vehicles, what happens to those vehicles after you no longer use them. Now, this is from the work of Santero and Horvath at UC Berkeley, biggest sources of greenhouse gas emissions. And the materials used, so the extraction and production of materials used for the construction, the overlay of pavements, and their transportation to the sites, from their sources to the sites. So this is on the overlay, on the agency side. On the user side, we're going to focus essentially on rolling resistance roughness. Just to point out, this is a logarithmic scale. So these smaller things here are not very significant. And there are other significant things. For example, the structures. This has to do with like vehicle tire to pavement interactions, things having to do with dynamic load and how the pavement itself is modified by the application of loads. While important is not the roughness question, and this is not something we're going to consider. All right, so that's the big picture. Now let me zero in on the problem of pavement resurfacing optimization. All right, so this is the first part where we're looking here simply at life cycle cost. This is the traditional approach to pavement management, except done with an optimization framework. So we're looking at these inputs: a roughness progression model, effectiveness model, cost of resurfacing, so unit cost, user cost, and our objective is to determine either the frequency of resurfacing or the trigger roughness at which you do resurfacing, and the intensity of that resurfacing, how thick your overlay needs to be. The objective is a minimization of life cycle costs only, LCC, over either finite or infinite horizon, and it's done. LCC here includes the entire series of user and agency costs. So, and the objective essentially, if you want, is to determine, this is a kind of traditional, typical sawtooth curve, showing roughness progression over time. Right, so roughness is on the y-axis. This is either time or the accumulation of loads. And then roughness increases, you do an overlay, it decreases, etc., etc. So the question is, what is the threshold? For example, what is that number, S2N, at which you overlay? And how much should your overlay be? That is, how low can you come? You can never go back to a new pavement. An overlay does not bring you back to that. You need reconstruction for this. But how low can you get? And so how often, so either how often do you do it, or what is the threshold, and then what's the intensity? So this is a standard nonlinear minimization problem with a series of, let me show the components, I will go through the notations, and basically you're minimizing the sum of the user cost integrated over time plus the agency cost associated with those overlays. You have an iteration model, which is that first constraint. So something that describes how the pavement roughness increases with time and as a function of the current state. You have an improvement function that describes how much down you can go depending on thickness and some initial conditions. The reference at the bottom shows the solution of this problem. And for an infinite planning horizon, not surprisingly, you end up with essentially a steady state solution after the first resurfacing. So a steady state solution which says that it identifies for you what is S2, that trigger roughness, or different types of pavements, of course, and it also identifies the level at which you should resurface. And it turns out to be quite interesting that let me actually skip this. It shows, this is a major insight from this research, is that the optimal strategy turns out to be to resurface with a fixed intensity. This is again for steady state conditions. And so constant traffic over time, no traffic growth, things of that, simplifications of this nature, that you resurface with fixed intensity whenever the pavement condition reaches a specific threshold, and the intensity you use is the one that achieves the maximum or the minimum possible roughness, because technological constraints prevent you from getting essentially to a new pavement condition. We also found, this is a slide I skipped, that the optimal solution turns out to be quite robust to uncertainty in the deterioration model. And that's an important result because much of pavement management systems today are actually based on probabilistic deterioration models, which is good. But for this particular problem, which is a small part of PMS, or pavement management system, that is not so important. There's an equivalent problem with a finite planning horizon, and described in the reference at the bottom here. And the insights are very much the same. That is, you do end up with a steady state solution, except at the beginning and at the end. And there's also a trigger roughness, and you resurface with a fixed intensity, which is which leads to the maximum possible reduction or the minimum resulting roughness. So again, there's robustness to uncertainty. Right. So this is how we go about coming up with these optimal policies that optimal trigger roughness. Now let's bring in emissions. So we said in the case of cost, there's a trade-off between agency and user. In the case of greenhouse gas emissions, there's also a trade-off, which is somewhat similar. So if you have on the x-axis the overlay interval, that is the interval between two successive overlays, and you look at CO2 equivalent emissions on the y-axis. So the higher the interval, obviously, then the user, the roughness emissions are going. The roughness emissions are going to, the longer the overlays, they're going to increase. Right? That is, if you do overlays every 10 years, your roughness is never going to grow very much, and therefore user emissions are going to not grow very much. But as you extend the period between overlays to something like 30 years, then the user emissions obviously are going to increase, while the agency emissions obviously are going to decrease. Somewhere in the middle, there's a sweet spot, and if your only objective in life is to reduce CO2 emissions, you would go to that global optimal, and you would use that as your overlay interval. However, there's the other side of the picture, which is costs. So that green curve I had a minute ago is, I now have it in pink, and on the same graph, again with overlay interval on the x-axis, I have, in addition to emissions, I also have costs, right? And if you look at the objective of life cycle cost minimization, there's also global optimal, which we saw using some of the methods I just briefly described, but that's very unlikely to be the same as this one. And so you have kind of an optimal span of optimal solutions between these 2 points. Clearly, it makes no sense whatsoever to use an overlay interval which is less than that point, because both emissions and costs are going to increase. To the right of that point makes no sense either, because they both increase. But what do you do here? What is the appropriate point in the middle? Now, because we don't really have a price on carbon currently in the world that everybody can agree to, we cannot turn these emissions directly into cost, in which case the problem would be trivial. But what this kind of optimal solutions gives us is essentially kind of a frontier of possible optima. This is what we call a Pareto frontier. And the Pareto frontier is described here with now emissions on the x-axis and costs on the y-axis. And what the frontier shows you is the set of optimal solutions in that optimal span, right? So essentially what you can do, you can never be below that frontier, right? This is the best that you can do, but you can certainly be above. Now we applied this concept to a very specific two-lane rural road in California, and what we find is that Caltrans happens to be doing a hell of a job. They fall on the frontier, at least with their current resurfacing policy. I always like to show this slide first when I go to Caltrans to put them in a good mood. And they're doing, again, this is a road in California, so there's no reason why the Washington State DOT policy would make any sense, and it doesn't. It's above the frontier. But then I show them what happens when we look at the two-lane urban road. And again, this is real data for specific pavement segments in California, and we find that they're so far off the frontier that I had to shrink the frontier tremendously so that I could show where they are. Right? So they're above the frontier both in the X and Y directions. So they're spending too much money and producing too much in terms of greenhouse gas emissions relative to what they would do if they were using an optimal solution approach to pavement resurfacing. Now it's important to realize that Caltrans actually doesn't use an optimization. They have this threshold of 2.7 liter per kilometer. Right? And so that threshold is not optimal whether in terms of cost or in terms of emissions. Where the policy they used to do earlier, they used to have earlier, isn't much better, but maybe somewhat better. Same kind of observations when you're looking at 3-lane rural roads. Again, Caltrans does very well there. If you extend that frontier, they're on it. And again, in urban roads, it's not a good solution. So, all right. So this is kind of how you bring in greenhouse gas emissions at the facility level. Caltrans really doesn't care about this because they're not concerned with managing individual segments, but with an entire system of pavement segments, tens of thousands of kilometers. And the problem is different because it's not sufficient to just take the optima from each segment and collectively use them, simply because you have constraints, you have system-wide constraints that mean, in particular, budget constraints that make it such that the collection of optimal solutions is not itself optimal, right? Even the budget constraint. So this is a narrow budget, a kind of constrained optimization problem. And what we're going to first talk briefly about is how we approach this problem, and then later how we might bring in greenhouse gas emissions as well. So again, going back to focusing only on cost, the approach we'll use, let me just say 2 words, is known as bottom-up. Okay, so most pavement management systems currently use a different approach, which is top-down, where we come up with an optimal solution, identify fractions of their network that should be maintained, and then let the engineers map those fractions to individual segments. Our approach is bottom-up in that we start at the segment level, and the advantage of it here is that when you start at the segment level, you can maintain the identity. You can use very detailed models of individual segments instead of some generic models that describe the entire network. All right? But then we go up, and now we have to face the budget constraint. It turns out this is a resource allocation problem, but let me kind of graphically express how it works. So let's say that we've used the optimization methods I described briefly earlier to identify thresholds for all these segments in the state of California or in certain districts. So the optimization gives us, as I said, a trigger roughness for each of these segments. And some of them deteriorate maybe faster or have a lower trigger roughness, some have a higher trigger roughness, etc., etc. Now, once you have that, ideally you want to add these things to go all the way to the network level, or the system level. Now, the first thing you realize that each of these trajectories of these sawtooth curves has a cash flow diagram associated, right? So, more or less, this is, the small arrows might be the user cost between overlays, and the big arrows are the agency costs associated with the overlays. So we can add dollars, and we might get at the network level something like this, right? The problem, of course, is that there's something called a budget constraint. And the budget constraint makes it such that in many years, typically in most years, you would not be able, again here I've shown only the agency cost, but the budget constraint would make it such that you could not apply the collection of optimal solutions. And what you need to do essentially is to reduce or to redistribute your expenditures over time so that you just use the budget and you use all of it perfectly. Now, how do we do that? Well, what we've done essentially to achieve this is to adjust the trigger roughnesses of the individual pavement segments up or down, right? So that what we end up with is something that, on a uniform basis, over time, matches the budget constraint. So the way that it's done formally is by solving this nonlinear minimization problem with the following constraints. Briefly, these are, the first one describes agency and user cost. This is the budget constraint. And then there are agency cost, user cost, etc. And this work is described in this paper cited at the bottom. I'll skip through the solution itself, algorithm, just to show you some interesting results. So this is what this shows. This is a kind of a case study using, I think, 350 pavement segments from District 4. District 4 in California is the district that includes the San Francisco Bay Area. All right. And what it shows, we varied the budget constraint on the x-axis, and we've looked at the trigger roughnesses we end up. The interesting thing, well, and this is a heat map. So the light colors show you there's a lot of solution points, and the dark ones is where you have fewer solution points. So in general, obviously, as you increase your budget constraint, as you have more money to spend, you can reduce, on average, your trigger roughness, right? You can do more resurfacing. But the other really interesting point is how broad that band of solutions is. Contrast this with what Caltrans is essentially doing, which is a single line, where we have here, essentially this is a probability distribution function, probability density function of solutions, right? With kind of the peak being here and the tails falling off there. Caltrans would be using a single line, single curve through that. So what this shows us is that the approach used by Caltrans of having this uniform trigger roughness is really not effective, and it's far from optimal. Now, obviously, in practicality, we will come up with a different trigger roughness for every single one of these segments, but we could classify this into different categories, because associated with each of these trigger roughness is a certain type of highway pavement, interstate versus state highways versus rural, etc. Again, though I'm not showing it here, it turns out the solution to the network level problem is quite robust to uncertainty as well. Right, so this is as far as life cycle cost minimization is concerned. Let's bring in now the greenhouse gas emissions. So again, what we're going to do here is approach this as a multi-objective, two-objective minimization problem. The formulation looks very much similar, but instead we're going to be minimizing cost, but we have now also a budget constraint in terms of emissions, if you will. So the way to think about this is that, let me show you this. The way to think about it is to think that I'm trying to minimize this, but I cannot exceed a particular emission budget, right? So similarly, we obtain a Pareto curve, right? And the Pareto curve gives us what is optimal to do at the system level. And what you see here, again, emissions on the x-axis, cost on the y, and you see how far Caltrans is for District 4 from what is optimal, right? And again, this has to do with the fact that they're using essentially that, first of all, they're not using an optimization method, but equally importantly, that they're using this single trigger roughness. So what can we do with this? Well, the first thing we can do with this is we can start talking about the price for carbon. Now, with every point on this curve, there's an implied carbon price, right? the slope of the tangent at any point here is effectively the implied price of carbon at that point. So if Caltrans or if the state of California were to decide that this is where they'd like to operate, with this combination of trigger roughnesses, then essentially the slope of the tangent at that point is the price of carbon. You can see that by the units are cost per ton, right, per metric ton. And so we kind of use some of the points that are found in the literature, the prices found in the literature. And so the first point is the California price, we call it. It's the price that came up in the second carbon auction done in California. So this is part of the cap and trade system. And it found that it's about $10 per metric ton. It's not very high, and it means that the solution that attempts to only minimize cost is not far from where California will be operating. We've looked at some literature, and there's a study done by Nittel and others that attempted to approach it more from kind of an environmental point of view and deciding what should be the fair price of carbon, and they were found to operate here. Their price corresponds to this point here, which is almost 10 times higher, so on the order of $100 per metric ton of carbon. Right? But essentially, if you were to look at the market, this then sets a price, essentially. If this is the price of carbon, then this is where you should operate. If society decides that this should not be left to the market, and there needs to be some other non-market mechanism, for example, like that represented by the red point, that is where you should operate. Some policies we can look at. So Caltrans has this approach that they overlay all the lanes associated with a pavement that reaches a certain trigger roughness, right? And one thing that they've been considering is to only overlay the rightmost lane. So typically the rightmost lane, which carries only most of the trucks on a highway system, is the one that reaches the trigger roughness way before the others. And so one possibility is to only overlay that rightmost lane, or the two rightmost lanes, those essentially with higher roughness. If they did that, then in fact, so the Pareto curve would look very differently, and in fact, they would be closer to something approaching optimality. Here's what would happen if technological improvements made it such that we could reduce the minimum achievable roughness. So the minimum achievable roughness is the roughness after the overlay. This is the kind of technological limit, right? So if there was a possibility of reducing that, right, through material technology improvement, then the entire Pareto curve would move from this. So this is a minimum achievable roughness of 1 IRI. If we could bring, as a result of an overlay, roughness down to 0.75 IRI, the whole Pareto curve would shift closer to 0, so thus leading to better optimal solutions. Reducing vehicle miles traveled is a good thing in its own right, but it certainly has a big impact also on our solutions. So this is the base case that we used in our work, and this is what happened if you had a 10% reduction in vehicle miles traveled, 20%. Now keep in mind, this point is not 0, 0, so these improvements are not as dramatic as they first look, right? But they're still significant, right? There's an alternative perspective, and in fact, our earlier work was criticized because it said, well, highway agencies are not really in the business of minimizing costs subject to a budget emission constraint. Actually, what they're trying to do is to minimize emissions as much as possible given their financial budget constraint. And this is maybe a more realistic approach where we reformulate the problem differently, slightly. Here we're minimizing emissions, and the constraint here on the x-axis of the other objective is the agency cost itself. No user costs are involved. You also can obtain a Pareto solution shown by the red curve. And so the problem is different. It's a different optimization problem, which is to minimize life cycle greenhouse gas emissions subject to a financial budget constraint. And here again, we can compare this to what happens, in fact, in California. And again, there's some distance between the effective solutions that we get using the uniform trigger roughness versus our optimal solution. I promised 40 minutes, and I'm almost there. Limitations, there are many. These are the two most important. We haven't looked at reconstruction. We are now, but we don't have results yet. That idea of constant traffic over time for a long planning horizon doesn't make sense. Should incorporate traffic growth and cost. Yes?
So, when you got into the idea of VMT change, that sort of played into where my question is going to go. I don't know that much about how pavement roughness is measured, but as a cyclist, the pavement at the edge of the roadway makes a very big deal to me. And I don't know of any studies that have been done, but I can imagine that people's perception of safety that is helping them make this decision of whether they're going to cycle or not could very much be tied to the roughness of the pavement, because you feel like, if I were to fall because this pavement is rough, who knows what's going to happen, that sort of thing. Right. So I wonder if you've thought of ways, or just immediately, if you could think of ways that you could actually tie cyclists into the equation as well, in terms of, what sort of roughness would be tolerable to them, whether the current measurements actually take into account the edges of the pavement, as well as sort of the user cost piece of it.
Okay, this is a good question. So the first, answering the second question, currently safety is not accounted for in this whole idea of when you resurface pavements, right? Safety is not a consideration at all. The consideration and roughness, in fact, while it does affect safety in the context of bicyclists, certainly has a very minimal impact, roughness itself, on on cars and trucks, etc. Throttling, which is a different mechanism, which is where you have depressions in the wheel path, this has a big impact on safety, much more than the roughness. So, could we do it? So it would have, the essential question is, can you associate a cost to safety? Right? Because these optimization methods are essentially meant to minimize life cycle costs. So if you can associate the cost to safety, then you can then bring that consideration as part of the life cycle cost on the user cost, right? If you can't, and of course assigning dollar value to a life is typically not something very palatable, then you'd have, and assuming this is important, in Berkeley, California, where all our students now are biking and half the faculty, I think that's a big deal to society. And in this case, you could possibly consider that as a different objective to maximize, in this case, maximize safety or minimize deaths or injuries or some combination. So it is feasible. It's depending on whether or not you have a dollar sign associated with it. It's a different approach. Yes?
So I have a general question about pavements that keeps me up at night, so I'm going to take this round asking an expert here to ask that. So one of the questions I have is that, like, after a snowstorm happens in the Northeast and there's potholes, gaping, let's say, safety issues that appear, I was wondering if there's any thought, or in the future, if you might be able to use like cell phones or looking at acceleration, deceleration of vehicles to be able to detect safety issues before, let's say, they're reported in, or when you've got that situation situation of triage, figure out how to triage. Either using, because that's like a pavement condition, I know it's extreme, but, it also presents, I would argue, some of the bigger safety issues.
Right. So, so this is interesting, and so I have a colleague at UC Berkeley, a group of colleagues who are looking at using cell phones for a variety of things. Obviously, to measure actual travel times, or to observe choices made regarding to travel, or to try to convince people to use different choices. I have, as part of that larger collection of colleagues, one of them is very interesting in applying that to pavements. And I think the idea here is very along the lines of what you're describing. It's like, if we have all this crowdsourcing of information for things having to do with crashes, or with travel times, or etc., why don't we have it for things having to do with major things like potholes? It's less of an issue on the coast, on the California coast, but certainly is an issue as we go up into the mountains, where freeze-thaw cyclones, in particular, have a very detrimental effect on pavement condition. There was one question here.
I have two questions. First question is regarding you just mentioned that the optimization result is robust to the iteration uncertainty.
Yeah.
It's clearer. Also, because in my opinion, I think other than the iteration model, also regarding the construction cost, even the green gas emission, a lot of uncertainty in that. So, do you think it's how to consider that in model? I think the second question is regarding the future research. You just mentioned that you're going to extend the overlay to full set of MINR. Because I have read almost all your paper in the past. I just realized that you.
What a waste of time.
Yeah. In your modeling, you only consider, for example, the overlay. So I know it's difficult to consider full set of MINR, especially for the payment calculation.
Yeah.
So I just want to learn a little bit what's the mathematical challenge in that. If we want to consider all the treatment methods in one formulation.
Sure. So regarding the first question, probably the highest source of uncertainty is actually those greenhouse gas emission factors. So not shown here, we've done a range of sensitivity analyses, and as you expect, this Pareto curve can move up and down significantly as those emission factors are modified. And so my colleague Arpad Horvath, with whom I've done much of this work in addition to several graduate students, has done a fairly significant amount of work, in particular with, I showed the slide earlier, with citation by Santero and Horvath. So they looked at that, and you could see here there were some uncertainty bands associated, right? So that certainly no question. But second, the unit cost of construction are actually much less uncertain than things like deterioration models, right? So deterioration models, it's not just, an uncertainty above a mean. It's also the fact that the entire model itself may have a different structure. We've used here kind of state-of-the-art, existing from the literature, roughness deterioration models. Not in the earlier work. The earlier work was purely a Markovian model, memoryless. But in the later work, we actually use models developed by Patterson and others based on very large data collection efforts that were then calibrated to US conditions by Shelty and his colleagues at Michigan State. So, but again, the very structure of these models, even though they're memoryless, there's also uncertainty that goes beyond uncertainty around the mean. There's you can think of this as epistemic uncertainty, rather than just simply stochastic or uncertainty which is inherent in the process. That is, we don't really understand how to best model roughness. Roughness is not like cracking where you can do experiments in a lab under controlled conditions, or rotting, right? Or you can run a heavy vehicle simulator on a pavement. Roughness is a collection of all of these. and so it's not something you can actually do in the lab, right? So
Also one issue, because right now since the not 21 the DOT they focus more on clean preservation.
right.
I think those activities will affect the deterioration model.
Yes, yeah. So you're pointing to a very important issue when we're using field data. That what we're observing is not just deterioration; it's a combination of deterioration and maintenance. And maintenance is not some random process. I mean, it's done in response to deterioration. So the data sets are not random. This is really less model as a system of equations, right? But leaving that aside, moving to your second question about incorporating. Now, if you're using these kind of discrete optimization methods, like used in some of my own research and very much of the pavement management systems in use today, use Markov decision theory, dynamic programming, it doesn't matter. You can represent all the various treatment effects very easily. Essentially, it's an optimization, there's a brute force optimization by brute force. It's fed to a computer, and it doesn't matter how large the size of the problem is, eventually you get a solution. These continuous time, continuous space, continuous state space approaches are essentially semi-analytical, right? And dealing with that, people have used optimal control in the past, approximating the sawtooth curve by continuous curve. That doesn't really work. These, discontinuities lead to very significant complications in the optimization because you can't differentiate, right? You can take a derivative at the discontinuity. So maintenance is simple because maintenance can be representing as a change in the slope, in the rate of deterioration. So you can feed that in, the maintenance intensity, routine maintenance, crack filling, sealing, patching, etc. Doesn't really affect surface. I mean, the effect is minimal. It changes the rate of deterioration. So that's easy. Reconstruction is a completely different story because essentially with an overlay, if you represent the overlay better than we've done here, in our latest research, we take into account kind of accumulated damage. So you don't really get to steady state solution ever. What brings you down, so to the initial state is reconstruction. So that mathematically is a more challenging problem. We have a paper that just came out in the European Journal on Transportation and Logistics, and it describes how to approach this problem. It's more tricky than what we have.
Yeah, very similar question is, we obviously use a continuous model, but from field data that you have, what fraction of the overlays are really associated with some type of proximate cause of a stochastic event, like a flood or a seismic event, versus what you're just accumulating damage? Do you really have a feel for which is the dominant process in California?
Right, so for overlays, it's really accumulated pavement damage. Events like flooding of coastal highways, and that's happened Highway 1, if you're familiar with it, then you're really talking about the reconstruction. Essentially, you had a slope failure, right? And the Highway 1 segment from Highway 1, south of the Bay Area, just washed down into the ocean. And there you have to reconstruct the slope, do a reconstruction of that pavement, something that took over a year to happen. So that's really not represented here now.
Just a quick follow-on, have you considered setting an upper limit associated with your steady state solution based on presence of these potential dispersion?
Yes. That's why not here, but we've done some work where we looked at seismic events. Obviously, California, that's something we worry about, and how pavement management would need or bridge management. Actually, we looked at a problem with bridges. How existing bridge management, if they were to consider the probability of seismic events and of complete destruction of the bridge, how that would change. So that combination of what people sometimes call latent deterioration and manifest deterioration, or catastrophic versus gradual, is actually a hot topic of research currently. There's several people working on it, and it changes the picture, of course, entirely. Especially when you look at things like bridges and seismic events, or in the case of the California coast, things like flooding and pavement.
Can I ask one quick question?
Okay,
Short.
good question.
Okay,
This is
so-
a class.
Yeah, so it's kind of pleasantly surprised that on the individual roads, that the rural road, Caltrans actually is on the curve, which seems incredible to me. But
Yeah, it did to me too.
but why do you think the urban roads was so different? Than
Well, so essentially, there's the only kind of semi-intelligent explanation I can give is that, remember, this is based on the concept, on very subjective criteria.
Yeah.
Caltrans engineers drive on these roads and say, oh no, this is way too rough, right? So, on urban roads, and in particular many of these are very heavy volumes,
Yeah.
those standards.
People
that they
complain
use-
more about
Pardon?
them. People complain more about them, so they get fixed more often. So it's
Yeah, I think, no, it's not so much that. I think, it's based on a panel of drivers, including many pavement engineers, right? So, the only thing that I can say is that when you're driving on urban roads, you expect a higher level, and therefore, no.
okay. Thanks.
Okay, since the next group, I think they're coming in for the class, so please